So we're looking at the description of half-life, and we see that every 5,730 years, half of this, whatever you have, becomes into nitrogen 14. And so by looking at the ratio of those two, we should be able to figure out how many years has passed. And because there's a certain amount of natural carbon 14 that's within your body, for example, right now. And if you were to die, I could look at how much carbon 14 is in your body, excuse me, a little bit later. It's allergies, guys. Um, and so we could see how much later, how much is left over by seeing that, usually I should have 12% of carbon 14, but now I have only 8%. So that means you could figure out how many years have passed by to make that many have gone from carbon 14 to nitrogen 14. So again, some definitions. The half-life of an element is the time it takes for half of the material you started with to decay. Every element has its own half-life. Every radioactive element has its own half-life. And that half-life is like really, really constant. Okay, it doesn't change. It's like a clock, keeping perfect time. Let's see some of this in action. So here's a grid, and every time you click on the PowerPoint, I'm not keeping it running it as on a presentation mode, then you'll see that more and more of these change. And so after half-life, 5,730 years later, you can see that half of the carbon 14 has now become into nitrogen 14. And then we go on next and we see now so much is nitrogen 14, and we only have 1/4 of the carbon left. And then we keep moving on, and now we see that it becomes half of that, and now we only have 1/8 left, and then so forth. And we can see how it decays over time, going from 10 to 5 grams, 5 grams to 2.5 grams, and then so forth. And that's amount of carbon 14 is decaying, is becoming less and less, and the amount of nitrogen 14 is increasing. And so again, here's a graph showing you what it is. The one that is becoming smaller, which is the carbon 14, is called the parent isotope. And then the one that we form is called the daughter isotope. The sources of radioactivity, again, you have stuff within Earth. So there's radioactive substances buried under the Earth that are always being produced. And then we have reactions going on in stars, and then high energy particles come flying from there, and they land onto Earth. Many of them are deflected by our Earth's magnetic field, as we saw in magnetism. And then we have human produced ones as well, of course, our nuclear bombs and stuff. Some naturally occurring sources examples, and some man-made sources examples as well. Radioactivity, is it a health problem? It sure is. It can alter your DNA because it has ionizing energy. It basically goes in there and makes ions out of your atoms, and then your atoms don't know what they are anymore. Uses of radioactivity, well, we use it for food sterilization, medical applications, smoke detectors, radiocarbon dating, energy, weapons, all of that fun stuff as well. And we don't really need to go into a lot of this stuff. You can see that in in one of these, and we don't use those anymore, but we used to back in the old days. They have changed now. But this particular isotope emits alpha particles that ionizes air in the space in the detector. The ions allow current to flow. If smoke is produced, that absorbs the alpha particles, interferes with the movement, and that creates an alarm. And that was an old way of using it. We are using different methods now for smoke detectors. We see them that we can use